Hi, this is our talk for approximating the center ranking under the Ulam metric for FSTTCS 2021. This is joint work with Dr. Diptarka Chakraborty at NUS, Dr. Kshitij Gajjar at NUS, and I am Agastya Vibhuti at EPFL. Okay, so I'll jump right into the real life motivation for our problem. Suppose there is an election in an office. There are 6 candidates: regional manager, assistant regional manager, assistant to the regional manager, head of sales, head accountant, and HR rep. The final election results will be essentially a mapping of these candidates to these 6 positions, and it will be a one-to-one mapping. Essentially, we want to produce a permutation of these 6 candidates. Now, the voters inside the office will have their own preference lists, and this preference list completely depends on their own and can be completely arbitrary. For example, voter 1 will nominate candidate 1 for regional manager, candidate 2 for HR rep, candidate 3 for head of sales, candidate 4 for head accountant, candidate 5 for assistant to the regional manager, and candidate 6 for assistant regional manager. Similarly, voter 2 will have their own preference, and so do voters 3 and 4. Now, as we see that since the voters completely decided this on their own, voter 1 has decided to nominate candidate 2 for only HR rep, while voter 2 ranks candidate 2 very highly and nominates them for the regional manager. Clearly, this will cause our final solution, which I'll describe soon, that what we actually need to find to have problems. Now, what do we really want to do? We want to produce a final election result so that no voter is dissatisfied too much. What do I mean by dissatisfaction? Intuitively, it means the following. After the results have been declared, each voter will make changes to their preference order in order to finally come to peace with the final election result. The more the changes are, the lesser a voter is satisfied. So in the final election results, we want to produce some permutation so that each voter has to make as less changes as possible in order to convert their own preference list to the final permutation or final election result. Clearly, since each of the preference lists can be different, it's impossible to simultaneously satisfy all of them completely. Thus, we aim to produce some election result which minimizes the voter's dissatisfaction. What could be a naive attempt? A naive attempt could be the following. We just pick some voter arbitrarily and copy their entire list without loss of generality. Say this was voter 1. Although this will completely satisfy voter 1, this may cause problems to voter 2 or so on. For example, let's look at voter 2. Voter 2 had ranked candidate 2 very highly, while in the final list, candidate 2 is actually at the bottom of the entire election. Voter 2 needs to pick candidate 2 and move to the bottom. This will count as one move. Similarly, candidate 6 is also nearly at the bottom of voter 2's list, while they are ranked quite highly in the final election results. So voter 2 would have to make another change to pick candidate 6 and move it to roughly the top. Thus, voter 2 made exactly 2 changes, and the distance, and we call this the distance between the voter 2's preference order list and the final permutation or the final election result. Now we formally define what distances between permutations are. For permutation P1 and P2, the Ulam distance is known as the minimum number of moves we require to change a permutation P1 to P2. In fact, this is symmetric and satisfies the triangle inequality. And further, the distance between a permutation to itself is 0. Hence, this is just not a distance function, but it's actually a metric. In this particular feasible solution which was provided to us by the naive algorithm, the distance of voter 1 to the final permutation or final election results was 0. Thus, voter 1 is completely satisfied. But all the voter 2, 3, and 4, they are quite dissatisfied, having to make 2 changes. Let's look at a smarter solution. For this particular solution, voter 1 has to make 1 change. So they are slightly more dissatisfied now. In particular, they have to move candidate 6 to roughly the bottom. But voter 2 is much more happier since they also have to make only one change instead of two that they were making earlier. So is the case for voter 3 as they move candidate 1 and voter 4 as they move candidate 4. Note that a change only consists of picking some symbol from their place and moving it to another place. It's completely fine to either move the symbol from the end, from the top of the list to the bottom of the list, or just move adjacent positions. They count as the same. In this particular feasible solution, we in fact obtain that each voter has to make exactly one change, and this is optimal. Why? Because since the lists were not same, at least one of the voters will encounter one change with whatever final list we produce. So even though we slightly dissatisfied voter 1, in reality, overall the harmony inside the office is maintained since each of the voters had to make exactly one change. This is much more balanced, and this is what we are looking for. What we are looking for, to be exact, is to minimize the maximum dissatisfaction. Even though one of them might be 0, or one of the voters might be completely happy, this is not very good for us, particularly if someone else is too unhappy. So it's better to balance the happiness in this sense. Now let's mathematically look at what I have been saying till now. So this problem is known as the center permutation problem. In particular, if we are given a set S inside a metric space of points, a center is a point inside the metric space, not necessarily inside S, such that it minimizes the maximum distance to the point of S. In reality, what are we doing? We are finding a point inside the metric space, not necessarily inside S, and drawing a ball around it. We want to minimize the radius of this ball. Mathematically, it can be seen like this. In our particular case, the M given points were the preference orders of each of the voters, and the measure of the distance was the Ulam metric, which essentially consisted of the minimum number of moves to convert a permutation to the final election results. But what is the allowed runtime for this problem? We're allowed to be polynomial in n, which is the size of the permutation. And we're also allowed to be polynomial in the number of points, which is m. So if I represent the size of S by m, we are allowed to be polynomial in n and m. This problem is quite similar to the classical k-center problem. The classical k-center problem has great impacts on approximation algorithms and has been vastly studied. Okay, but there are subtle and very important differences between our setting of clustering and their setting of clustering. In the k-center problem, we want to pick points inside the metric space such that the distance of a point to its closest open center is minimized. In particular, they will have to pick k points and k balls will be drawn around those points, and we want to minimize the maximum radius. The runtime is allowed to be polynomial in the size of the metric space. This is where the clear difference lies. We are only allowed to have in our setting a runtime which is polynomial in the size of set S and the size of permutation n. Clearly, in the k-center setting, if k was equal to 1, we could just go over all the points inside the metric space and see which one did the best. This is brute force. This works because the runtime is allowed to be polynomial in the size of metric space. This won't work for us because in our case, the size of metric space is in fact n factorial. Why? Because the permutations are on length n. In fact, the size of m can be much smaller than n factorial. Now, just like the k-center problem has an analog, which is known as the k-median problem, which is a min-sum analog of the min-max variant, which is k-center. Our problem, which is the center permutation problem, also has a min-sum variant, which is known as the median permutation problem. There is another difference with the classical clustering k-center, k-median to our setting is that the k-center problem is usually considered to be simpler than the k-median problem. In our case, it's exactly the opposite. In our case, the center permutation problem is considered to be much harder than the median permutation problem. To give an idea about this, I will give you a background of results and tell you about the questions we tried to answer and why we decided to answer them. To start with, there is a folklore to approximation for any arbitrary metric for both the center and the median problems. It's not very hard to see, and in a couple of slides, I will give you the intuition behind this. To start with, let's look at the easiest metric, which is the Hamming metric. For the Hamming metric, the median problem, in fact, lies inside P. Now, this really answers the question that why center permutation problem is harder than the median permutation problem, because even for Hamming metric, the center permutation problem is NP hard. But there's a p-task. There's another metric which is very similar to our metric. It's known as the Kendall metric. The problem is NP hard for both the median and the center problems, and there's a p-task for both. For the Ulam metric, for the median problem, it's not known to be in P, or it's not known to be NP hard. And a less than 2-factor approximation algorithm was only broken in Sora 21. This is very recent. For the center problem, the problem is in fact established to be NP hard, but a less than 2-factor is not known. One thing which we haven't considered so far is that we had no direction in how to start breaking the 2-factor for general M. But let's look at the following thing. For the Kendall metric, the problem is NP hard even for constant M's. This gives a strong belief that the problem in fact might be NP hard even for constantly many strings, for the center permutation problem for the Ulam metric. And no progress had been made on breaking the 2-factor even for constantly many M. So this is where the line of our work lies. It tries to break the 1.5, it tries to break the 2-factor and gets to a 1.5 factor for constantly many strings or constantly many permutations. So this is the final result. There is a deterministic algorithm that takes a set S of M permutations on N as input and outputs a 1.5 approximate Ulam center in running time n to the power M square log M. Further, we also prove that for 3 strings, there is a deterministic algorithm that takes a set S of 3 permutations on N as input and outputs their Ulam center in polynomial N time. So this completely rules out the fact that for 3 permutations, the problem is NP hard. Let's give an intuition for the 2 approximation algorithm for the Ulam center. The same algorithm will work for Ulam median with only a slight change in the analysis. What does the algorithm do? Nothing. We can pick one of the points arbitrarily. How will this help us get a 2 approximation? Well, triangle inequality. Consider any point without loss of generality. Let's say we picked P1 and output it. The distance of any point to P1 is at most the distance to P star, which was the optimal Ulam center for this instance, and the distance of P star to P1. By triangle inequality, we can see that the distance of each of the individual distances of P1 to P star, and let's say P6 to P star, was at most opt. This gives us 2 opt. Now let's give some intuition behind how to compute the center. We're trying to shoot at a target. We're aiming for the bull's eye, but we are not an expert. Each time we try, we will miss, but we will try to recalibrate. Note that the recalibration cannot be arbitrary. It cannot be done naively. We have to keep trying to balance all the distances to minimize the dissatisfaction of everyone. We cannot do like we did in our very first example of completely copying the preference ordered list of one of the voters. We have to smartly improve on our final election results slowly so that each of the voters are quite similar to the final election result. Slowly we will get around the center. Even though every one of our hits completely miss the center, we will still end up being quite close. Now let's come to some applications before we give a high-level overview of our algorithm and our analysis. As we've already seen, the selection of candidates by voters, which is a question in the social choice theory, has been solved by this problem. Further, there are applications in speech recognition. In particular, what we might try to do is that the computer might try to guess an exact pronunciation of ours. What we will do is that we will record one of our texts through our speech. The computer will see a speech pattern and try to reproduce it. This is the center, what they're trying to reproduce. This can go very bad, and so we will record again. And then we will record again and again and again, and the computer tries to recalibrate till it comes with some pronunciation that's kind of same to ours. Now, similarly, there are applications in computational biology. The snapshots of DNA cannot be completely read, and we will read only portions of them. They will be considered as permutations, and we will need to find here two centers instead of one. This problem is similar to ours, but it's not exactly the same. The two centers represent essentially the DNA sequence of the parents, the mother and the father. High-level overview. The high-level overview is the following of our algorithm. Instead of directly trying to go ahead and get a permutation, first we will solve a relaxed version to it. The relaxed version will relax the constraint that the solution needs to be a permutation. How this will help us? This will help us in the following way, that in fact, we can write a dynamic program to compute exactly a solution which is not a permutation, but this will be an exact solution. The dynamic program will be exponential in m, but since m is constant, this is still polynomial in n, which is the size of the permutation. So we have our input. We solve the relaxed version through a dynamic program where we get a center string, but not a center permutation. This center string might have multiple occurrences of some characters and might have some characters missing in fact. Why are we able to write such dynamic program? Because such a dynamic program is a direct consequence of the dynamic program of the KLCS dynamic program. KLCS is the problem of computing the LCS for k different strings or k different sequences. A very similar dynamic program will lead us to our solution. The phase 2 of the solution will consist of converting the center string to the center permutation. This is a rounding step in some sense. The first part of the phase 2 will consist of deleting duplicate characters, and the second part will consist of adding missing characters. Finally, we have a center permutation. This is center permutation we will prove to be 1.5 approximate. So thus, to summarize phase 1 and phase 2, in phase 1, we will find the center string of length n in polynomial time. In phase 2, first we will check if the center string is a center permutation. If it is, then we are done. And in fact, we will have an exact solution, not even a 1.5 approximate. In the other case, we will delete and insert. So this is an example where the dynamic program ran on these input instances and gave us 1 to 1. Naturally, 1 is repeated twice and 3 is missing. So we delete 1 and insert 3. But later we'll see that how we will do it in a balanced manner. So suppose these were the strings and a dynamic program gave us S star. Clearly, we can see that the symbol 2 has been repeated at least 3 times. Now, what do we do next? What we go ahead and do is that for each of the strings S sub I and S star, we compute their LCS. Between S sub I and S star, we will compute an LCS and fix an arbitrary subsequence in both which match to those LCS. First, we observe that a common subsequence is essentially a matching of the indices such that the two matched indices have the same value and no edges cross. This thing can be seen in the following example. Here, we fix the LCS to be 2, 5, 3, 1, 4, and 7, 6. And this is the matching produced. Note that some other thing could also have been produced, some other indices of subsequence for S star, because S star has multiple occurrence of characters. But now we have decided to fix this particular one, and we will stick to this till the end of the algorithm, until the end of our analysis. After we have done, we mainly have the task of deleting the multiple occurrence of characters. But where does the problem lie? The problem lies that we cannot arbitrarily delete these multiple occurrence of characters because this might dissatisfy voters here and there. although it might satisfy some particular voter completely, we don't want to dissatisfy voters here and there arbitrarily without any control on them. So we will do the following thing. We will partition the occurrences of the characters. The first occurrence of each character will go into partition 1. The second occurrence of each character will go into partition 2, and so on. To this end, we will refer to the partitions as colors to avoid any confusion. So in our particular example, partition 1 has been referred to as color yellow. Partition 2 is color blue. Partition 3 is color green. Now, for each occurrence, for example, partition 2, for example, partition 1, and let's take symbol 2, it might have matched to some string. In our particular instance, 2 of partition 1 matched to every string. We will look at the string SI and see what characters were matched to S star. For those characters, we will color it with the same color. We will color the characters in the same color, and the same color will be the color of what? It will be the color of the character in S star to which our character in S sub I was matched. The other characters of S sub I will be uncolored. We can model the following matrix through this. The columns of the matrix will represent the repeated symbol and the rows will represent the strings. The I, jth index of the matrix will represent the color. What color? It will represent the color with which we colored the jth symbol of the jth repeated symbol of string S sub I. Note that for each column, we need to pick one color exactly. We need to retain one of the occurrences for each repeated symbol. And we need to delete all the other occurrences. So this is the following problem. We will need to pick one color per column so that the number of unpicked colors per row are minimized. What does this correspond to? This directly corresponds to the fact of minimizing the dissatisfaction of each of the voters, because deleting their color in a particular column means that we actually decrease the LCS and in terms increase the Ulam distance. This problem is a problem which we call the matrix bicoloring problem. We are given an M cross N matrix. Each of its M cells is either colored with a color or marked X. Why will it be marked X? Because some of the repeated symbol might not occur in the LCS of some strings. For example, in our particular case, symbol 7 did not occur in the LCS of S2 and S5. Entries marked X are never touched. A bicoloring scheme is a scheme which picks one color, exactly one color per column. It retains all cells of that color in that column and recolor everything with the color red. We want to minimize the maximum number of red entries or unpicked entries in each row. So for example, if we picked yellow for column 1, green for column 2, yellow for column 3, blue for columns 4 and 5, yellow for column 6, and blue for column 7. In that case, we delete all the other colors and we fill them as red. That will lead to row 1 having 4 red entries, row 2 having 2 red entries, and so on. In particular, we get that the maximum number of unpicked or red entries was 4. Computing a bicoloring which minimizes the maximum number of red entries is in fact NP hard. However, we can give a dynamic program to solve this, which goes through the columns one by one. And yeah, it's not too hard to come up with this dynamic program. So what have we exactly been doing? In phase 1, we solved a relaxed version through a dynamic program. In phase 2, however, in phase 1, since we solved a relaxed version, we actually lost nothing. In phase 2, we first delete duplicate characters through a dynamic program. But this is the best possible way in which we could delete duplicate characters, because the dynamic program gave us the optimal solution. Then we add back characters and we again lost nothing. So the only way in which we lost anything was the deletion of characters. But this was the best possible way. So this does not tell us any way on how to bound it. So how do we actually bound it? We use the probabilistic method. Let Fj denote the number of distinct colors in any column J. We will prove through the probabilistic method that the maximum, that the objective function of this entire matrix bicoloring problem is exactly at most summation 1 minus 1 by Fj plus some tiny amount. How will we, what is the rough intuition of doing this? The rough intuition of doing this is the following. For each column, we will pick a color uniformly at random amongst the colors available. The probability that a color is not picked is exactly 1 minus 1 by Fj. And for each row, we will sum them up. A simple Chernoff plus union argument gives us that with non-zero probability, the objective function of matrix bicoloring is the thing which we have claimed on the slide. So this is the formal proof in terms of math. Since the expected number of red entries in any row is 1 minus 1 by Fj, we are able to apply the Chernoff bound on this. Why we are able to apply the Chernoff bound? Because these random variables were independent since we picked the colors for columns independently. Now we have essentially deleted all the things that were not picked. Putting everything together, since each repeated symbol occurred at least twice, this entire quantity can be bounded by at most half times the number of things which were missing. This eventually leads us to us having a 1.5 approximation since we lost a factor of half at most. One thing to note is that the matrix bicoloring problem which we stated has a lower bound of 2 minus epsilon. That is, we also proved in this paper that there is no deterministic 2 minus epsilon approximation for the matrix bicoloring problem unless P equals to NP. This proves that this method is completely complete on its own, and this cannot be used to prove for a general M. Since if we take this kind of route, we will have to delete characters, and each of the steps inside this algorithm will have to have a less than 2 factor if we need to break the 2 factor. But we cannot break the 2 factor for this step, hence this cannot be used. The conclusion is that we don't really know still if the problem is NP hard to solve for constantly many M. Or is there a polynomial time algorithm for general M that breaks a 2 minus epsilon factor? Further, the problem of multiple centers is still open. Thanks.